Okay, so topics for Monday's midterm. All right, so for rejection sampling, I would give a target PDF and a proposal distribution, and you need to find the M, okay, so that you can use the proposal distribution. And then you'll find the expected acceptance rate. And then you will provide, and I will provide some random values of Y drawn from the proposal distribution, along with some random values of U from 0 to 1. And then you will tell me what my resulting X values will be. Okay. All right, are there any questions on this? Does that make sense? We're all good? Okay. And then, what's going on with my computer? Save. And new sketch, okay. All right, and then, all right, we've got Box-Mueller. All right, Box-Mueller. All right, so if I give U1 and U2, you return Z1 and Z2, okay? And then it will have a bivariate normal, okay? And I'll provide a desired mu and sigma, okay? You find vector B and matrix A, okay? And if I give Z1 and Z2 coming from normal 0, 1, you give X, X1, X2 coming from normal mu sigma, okay? Okay, are there any questions on this? Yes.
Are we going to test mixture and
No, I don't have any mixture distributions on there. And, I'm not planning on having any convolutions. So what we got here. Okay, and then lastly we've got Monte Carlo integration, just the uniform case. Okay. I'll provide h of x, okay? Well, I'll provide the desired integral, which will be I is equal to a to b of h of x dx, okay? And then I'll provide, I'll say a small sample of u drawn from uniform A to B. And then you return estimate I hat. And I think I'll keep h of x simple, and you also find the theoretic I with Viet traditional integration. Right, and then so h of x will be kept simple. Okay, so either a polynomial or, yeah, I'll just keep it a polynomial, right? We know how to integrate polynomials, okay? Okay, is that all right? Small sample U, yeah, all right. So there's so no code, it's all mathematical, but there is gonna be a lot of like calculations. So you definitely need a calculator because I'll provide like a random U and you're gonna have to plug that into your calculator to get, you know, whatever it is that we're looking for. Yes?
So is graphing calculator okay?
Yeah, graphing calculator is fine, okay? Yes, question?
So for inverse CDF, you give us PDF, right?
Yeah, I'll give you a PDF. Huh?
We use integration to find.
Yeah, you'll need to integrate to find the CDF, yeah. Okay. So you need calculator, definitely, all right. And then, all right, that should be it. Okay, questions? Yes.
So this covers up to Monday?
Yeah, it'll cover up to third week Monday. Okay. Yeah.
So for the multiplier is given 1 and 2 and 2 is already value of 0 to do that.
No, so this is like, if I throw this problem on there, it'll just be like, here's U1 and U2, what's Z1 and Z2, right? And this one will be like a 5-point problem, right? You just plug in the numbers and plug it out, right? So, yeah. No, this covers it all, okay? Yes.
How many questions?
I don't know, whatever that. Right? It's probably like 4 questions, but each question has like 4 parts to it, so I don't know what that is, okay? Yeah.
So important sampling is not there.
Yeah, important sampling is not there, right? Third week Monday, so we covered up to Monte Carlo integration, the uniform case only, okay? Because on Wednesday we covered Monte Carlo integration, the general case, and then we started covering important sampling, yeah. Okay. All right, any other questions? Okay. All right, let's continue on here. Well, are there any questions in general before I go on with important sampling? Homework stuff? It's okay? All right, I guess so. Okay. All right, so we left off talking about importance sampling. And the idea is, again, I want to call this weighted Monte Carlo integration. The idea is we want the expected value of some function h of x, or x is drawn from f, okay? X comes from the distribution f, and this is equal to h of x, f of x, dx, right? Okay, but we cannot sample from f of x directly for whatever reason, okay? So what do? We will sample from g of x instead. Okay, and so what happens is we're going to sample from h of x, and then we will divide by g of x, but multiply by g of x, okay? So the value of our integral remains unchanged. So this is still expected value of h of x, where x comes from f. Okay, it's still this. But we say, look at this. Here we have a function, and here we have a PDF. And so we rewrite this in the form, well, this can be rewritten as the expected value of g of h of x times f of x divided by g of x. Okay. Okay. And all right. So what we do now is this thing can be called the importance weight. And basically, the steps will be, we draw x 1 and 2 all the way up through xn. These will come from g of x, okay? And then we calculate this thing, h of x1 times f of x1 over g of x1, and then h of x2 times f of x2 over g of x2, etc., etc., etc. Okay, and then lastly we take the sample mean. Which will to approximate our desired quantity. Okay, and the idea was that in certain regions, by drawing from g of x, we will sample these particular values of x too often, and so those values are weighted less because f of x over g of x will be less than 1. Okay, so certain values of x will be sampled too often. Okay, this happens when g of x is greater than f of x. Okay, certain values of x. Okay, but those values are weighted less. Okay, because f of x over g of x is less than 1, okay? Other values of x are sampled not enough, Okay, so this happens when g of x is less than f of x, okay? Okay, and those values are weighted more because f of x, your importance weight, is greater than 1. Okay, so let me compare this. Let me compare importance sampling to rejection sampling because they're similar concepts, but they are different, okay? Let's recall rejection sampling. All right. What is the goal of rejection sampling? The goal is we want a sample of x drawn from f of x, right? But again, the problem is we can't sample from f of x directly. All right, so what do we do instead? We sample from g of x instead, okay? But each of these values are proposed, and they don't necessarily end up in our sample, okay? We sample from g of x instead, but these values are simply proposed and are not yet in our sample. What has to happen in order for them to end up in our sample? Yeah, we accept if u is less than or equal to f of x divided by m times g of x. Okay. Now let's, and so let me just kind of illustrate what this could look like. Let's say, I guess we can look at the folded normal thing again. And okay, so we've got all right, this is not a good picture, but okay. This is our proposal, and this one is our target. Okay. So let's say we draw this value of x. Okay. With rejection sampling, we might accept this thing, we might not, okay? We would accept this value you know, with a probability, yeah, I'm eyeballing this, that looks like 70%, maybe. Okay, so we're gonna accept this with a probability of something like 70%. Okay. What we would do in importance sampling, and it's not really sampling, it's just that, so with importance sampling, we propose this x, we draw this x, and we're going to use this to help us estimate the integral, because we don't actually care about the actual values of x, we just care about the evaluation of our integral. And so in order to kind of compensate, we will just weigh this value towards our integral with a weight of 70%. We will use this value to help us estimate the integral, but weigh it to be 70%. Okay, so with because if we didn't have importance sampling, we could, because importance sampling, we said we are not able to sample from f of x directly, right? Now, technically, that's not true. We can always use rejection sampling and then end up with a sample of f of x and then use that, right? But in rejection sampling, we might have thrown away, we might have rejected maybe 30% of our numbers or 40% of our numbers, okay, that we proposed. And so what importance sampling does is says, you know what, I don't want to throw away 30% of my numbers that I propose. I don't want to throw away 40% of my numbers. Can I still use those? And importance sampling says, yes, we can still use those, but what we have to do is we are going to weigh these values less and weigh these values more, or something like that, okay, in order to compensate for the difference between f of x and g of x, because we're sampling from a different density. Is it okay? All right, let me, okay, so let's just kind of explore what this could look like. All right, so all right, so we'll do our example, we'll do another folded normal example. Okay, so our desired f of x is going to be basically the positive half of the normal PDF. So that's going to be, because it's only half and it still needs to integrate to 1, it's going to be 1 over root 2 pi e to the negative x squared over 2. Okay, for x in 0 to infinity. Yeah. Okay, and then our proposal distribution will be g of x will be the exponential, and to change it up we'll use exponential with lambda equal to 2. All right, and so this, so g of x is equal to 2 times e to the negative 2x. Okay, and all right, so what's going to happen is to estimate, let's say we want to estimate the mean, the expected value of this thing, okay? Okay, so this is equal to the mean of f of x, right? The expected value of x, if x comes from f, all right? So in this case, we have the expected value of f of x is equal to the integral over, in this case, our domain goes from 0 to infinity of x times our normal PDF, or our 2 over root 2 pi e to the negative x squared over 2 dx, yeah? Okay, so in this case, f of x is what we had before. And what's our h of x? Our h of x is just x, right? Okay, we rewrite this to be x, and then we've got 2 over root 2 pi e to the negative x squared over 2 divided by, and then I've got 2 e to the negative 2x times 2 e to the negative 2x dx. Okay, so I'm just multiplying by 2 to the e to the negative 2x divided by 2 to the e to the negative 2x. Okay, so that doesn't change the value of my integral. Is that okay? All right, and so let's go on to the next page. Okay, so now I've got the expected value of g of this mess, x times 2 over root 2 pi e to the negative x squared over 2 divided by 2 e to the negative 2x. Okay, let me see if I can clean this up a little bit. All right, so this is going to become x 1 over root 2 pi e to the negative x squared over 2 minus 2x, or plus 2x. Is that okay? So I should say expected values of g of this thing. All right, okay, so to estimate basically the expected value of expected value of x, okay, over the distribution f, what we will do is we draw x from g of x, okay, and then we calculate this thing, the basically the h of x, f of x over g of x, and then we take the sample mean. Okay. All right. So the theoretic value, just so you know, theoretic value of kind of the expected value of x for f is equal to square root of 2 over pi, which is something around 0.7979. Okay, so that's our theoretic value. Let's go ahead and try this out in R and just kind of see what happens. Now in R, it's like trivial because we can actually sample from the random normal. All right, so let's see. All right, let's do, so this is a little wasteful, but what we're going to do is we'll get to kind of a positive normal will be R norm. Okay, wait. Random Z will be R norm N, okay? So I get a whole bunch of, I get a million random normals here, and then we'll do a positive Z. I'm just going to subset random Z, where random Z is greater than or equal to 0. Okay, and then we can ask, what's the mean of positive Z? Oops. Here, let me just set C1. Okay. We'll ask for a million of these. This is not working. Oh, rand Z. Okay, that's why it's not working. Okay. Okay, and then so when we do this, we get something pretty close to our theoretic value of 0.7979, right? Okay. I think actually, what is the square root of 2 over pi? Okay, so it's actually very close to the theoretic value. Okay, and that's if I sample from the normal and I throw away half of them and I just take the mean of what's remaining. That's exactly what we were aiming for, right? Okay. This time, what we're going to do is our f is going to be 2 times d norm. Okay. Our function, it's a function of x, and it's going to be 2 times d norm of x, all right? And our g is going to be the exponential. It's a function of x, and it's the exponential of x where the rate equals 2. Okay, and then and our h of x is just x, so I'm not going to bother with that. Okay, so what I will do now is I will do x will be drawn from r exponential. I want n of these things with a rate equal to 2. So I've got a million values of x. Okay, and then what am I going to do? I want to do x multiplied by the weight, which is going to be f of x divided by g of x. Is that okay? And what do I do with all of these things? I just take the mean of all of these things, right? I hope this works. All right. And we get a value pretty close to exactly what we were expecting also, okay? And that's basically it, okay? So here the idea again is we are not able to draw from, like, of course in our example we're able to draw from the normal directly, but in this case we're saying we can't draw from the normal distribution directly. I have to draw from the exponential distribution. And so we take each of these values. X is drawn from the random exponential, but we are going to weigh each of them by its importance weight, which is going to be the ratio between our desired density divided by our proposal density. And let me just see if this. Yeah, we get pretty good values. I mean, I don't know if this gets any better. It's going to take a while to crunch all of this. Yeah, okay. it's about as good as we can hope for. Whereas over here, yeah. So everything's kind of on the order of, or off by, 1/1000th of a point here, less than that. Okay, so they're on the orders of 10,000ths of points. Okay, all right. Yeah, this code is super simple, but it's actually quite useful in trying to estimate things. Yes.
Wasn't he like too far off on estimation?
No, these are just totally arbitrary. So yeah.
I mean, like if we were doing it like for the process, what would you do? Like off by 0.1.
Yeah, there's not a good number to give you. Yeah, sorry. Yes.
Why do we draw for x for the exponential?
Because we're in this case we're pretending that we are not able to sample from the normal directly. Okay,